Hi everybody, Angus here in our PSYC 218 class, Analysis of Behavioral Data, and we are doing our last chapter of the course, Chapter 14, Correlation and Regression. So this is another long chapter, just like Chapter 12, and what you see in the screen in front of you, I'm just using the full screen this time, there's no need to see my face for this one, is all the slides that you would see in the Google Slides PowerPoint slide thing. It has 68 slides in total, and when we go to our learning outcomes, there's quite a few things to cover this time. So if you remember from Chapter 12, there's only like 5 learning outcomes. In Chapter 14, there are 10 learning outcomes. So one thing I'd like to say to you for Chapter 14 is you may have done correlation before, and that's great. It will really help you understand this chapter. And if you remember stuff from ANOVA when we analyze variance, this stuff will help you go through Chapter 14 for sure. Seeing the 10 outcomes here may overwhelm you, but just remember, we can group these outcomes together, which we'll do later on, into several parts. So for part 1 today, we're going to go through our first outcome for sure, which is to describe the Pearson R as a measure of relationship between two variables, as well as outcome 2 using Pearson R as a definition and computational formula, and then finally interpreting Pearson R and explain its limitations and assumptions. Okay, the first 3 outcomes we're going to do for sure in our part 1. Before we move on to our lecture, we are going to go through the stuff you need to go through this chapter. Again, your Canvas course has been updated. We have Blue Jeans now, and then this is for Alexander College. Alexander College uses Blue Jeans, and I've included a link right here. So in the course front page or home page, once you click it, you'll go to Blue Jeans. In the previous video, I've shown you that in the page overview. And again, if you're lost, you'll find Blue Jeans link right there. More importantly, the announcements are updated as well. So we have 2 announcements. One, it's the announcement for Chapter 14. I've said it this time, so the announcement looks, if not exactly the same as the module itself, so you don't really miss anything. You can always go to the modules to find the chapter content, but this time, just to make sure you get it, it's in the announcement as well. So if you read on in the announcement, it tells you, hey class, let's finish our course of Chapter 14. It's got our video update, and we have the lecture slides, which you're seeing right here, along with the web tutorials, which you would use in either Microsoft's Edge, which is its Internet Explorer, or if you're using an Apple machine, use Safari. Chrome doesn't support Flash, so you're going to need to use Microsoft Edge or Safari. And then the glossary and flashcards, they work on any browser. So that's your first announcement. Your next announcement is the practice worksheets. So you can view that as well. And there are 2 worksheets that you can use right away. These are your Chapter 14 worksheets. It's very similar to Chapter 12 where we have concept questions and some practice questions. For our concept questions, they're on the Google Sheets. Again, there's a practice sheet along with the sheet with answers. Again, I recommend you doing the practice questions first as you follow along in these videos or going through the textbook or slides. Checking the answers in the answer sheet just to double check your work, or if you're learning, hey, know what the answer should be and try to figure out from there. You would also use your formula sheets as well in the statistics resources section. You can go into page 2 and here summary of statistics formula page 2, and you will be using the Spearman correlation, that's later on, but first we're going to use the Pearson correlation R and we'll explain that in our lecture, as well as the regression, which is later on in the next 2 videos. You'll be using a t-test or an f-test to test whether there is a correlation between 2 variables, but we'll get into that as well. Don't forget, there are other worksheets that you can work on for practice questions. So back to your Chapter 14 announcement with the worksheets. Here is a linear regression and correlation exercise that you can use. Again, you can follow along. It's an external link for the website. Work on these questions. Do the practice you'll need to complete the chapter. Again, all these links work along with resources like another textbook. If you haven't purchased a textbook from the college, we have lots of free resources that you can use. And then here's the last one, another review of correlation and regression. Like I said before, and I'll say it again, some of you can teach yourself this, which is great. More than half of you would need this help. This is why we have these videos to help you along. If you have any questions during this week, you can email us, email me on the college email, or message me on Canvas, or leave a comment in the YouTube video. That works too. Okay. So here we go. Let's start on the first part of the video lecture series on Chapter 14, Correlation and Regression. Okay, so correlation and regression, they're related in the sense that we're looking at how 2 variables covariate in terms of covariance, not just how each variable spreads or changes individually with its own group, but also how both variables vary, or you measure their covariance at the same time. Regression is a way to find the regression line between the 2 variables to see their covariance and making a prediction about where they're going to go. So, for example, if you got a positive correlation, this may bring you back to your research methods. So as one variable goes up, maybe, I'm just going to make it simple here, time and your age. As time goes forward, your age goes up. So that's a positive correlation. In fact, it's going to be a pretty perfect positive correlation. And so you can see there's a trend, an upward trend, that is as time goes up, age goes up. Correlation measures the degree and strength and the direction of the relationship between 2 variables by measuring their covariance. And regression creates a mathematical equation, a line. For linear relationships, it's going to be just like your slope formula. And it's based on this, along with covariance, looking at sum of squares, to make a prediction and look at the trend of how the 2 variables covariate. Okay, so that's going to be the gist of Chapter 14. We've tested individual samples against the population. We have tested independent samples with each other. We have done that in pairwise comparisons in t-tests, and we have done that for multiple pairs in ANOVA. And now we're going to do correlation and regression, looking at how the 2 variables relate to each other or correlate to each other using this method. There are 10 learning outcomes in this chapter, and we're going to group these outcomes together. So in our first part, we're going to do at least the first 3 for sure. So we're going to look at Pearson R as a measure of correlation between 2 variables. We're going to explain and identify how the Pearson R works to measure the relationship between 2 variables. We're going to calculate Pearson R using the definitional and computational formula. Again, these words may remind you of the sum of squares, definitional and computational formula. It's based on the same concept. And finally, we're going to interpret Pearson R and explain its limitations and assumptions. Again, the big one for this number 3 learning outcome is this idea, which I'm going to write it down. Correlation does not necessarily equal to causation. So, for example, you're going to see this in the slides, so I'll just tell you. You can close your eyes and think about this. For example, as the number of ice cream shops go up, in the slides it's going to say churches, but I'm going to go with ice cream shops because I'm thinking of ice cream, and the crime rate. So as number of ice cream shops go up, ice cream sales go up, crime rate goes up too. So does that mean, because there's a correlation, a positive correlation between ice cream sales and crime, that ice cream causes crime? You probably think no, and you're right. There's probably something else, a third variable that can explain this, explain why these variables, ice cream sales and crime rate, go up. Maybe it's the temperature. As the temperature goes up, as the weather gets nicer, more people are outside. If more people are outside, that means the homes are empty. If the homes are empty, they're probably more liable for breaking in. So again, people are outside, the weather's hot, they're probably going to get ice cream because the weather's hot, and because they're outside, the homes are probably empty, more homes anyway, and so more homes are liable for breaking in. So the idea that correlation does not necessarily equal to causation is going to be one of its limitations. We're going to explain this in detail in the next slides. Your next outcomes would be, testing the hypothesis of whether two variables are related or correlated to each other. We're going to look at other ways of measuring correlation using the Spearman correlation coefficient, the point biserial correlation coefficient, or the phi coefficient for two dichotomous variables. For our course, we're going to use two measures specifically. We're going to look at the Pearson R for linear relationships between two variables and Spearman correlation coefficient for ranked variables, that is ordinal variables. Okay, so variables measured in an ordinal scale, as in ranks. The point biserial and the phi coefficient will be covered in another course, but we're going to show you at least that these are other ways of measuring correlation between variables. As you know, there are different types of scales for different variables. You may remember things like the ordinal scale, the nominal scale, the interval and the ratio scale. For now, we're using Pearson R and Spearman correlation coefficient, measuring the interval ratio or ranks with the Spearman correlation. Finally, we're going to look at the linear regression equation to predict y values if the variables do have a correlation, and then testing the significance of that regression equation. So let's begin with at least the first three learning outcomes. The tools you're going to need for this are the sum of squares, which you should know by now, and this is where we get our computational and definitional formulas from. Your z-scores or z-scores, which you'll use for your hypothesis testing in Pearson correlation or Spearman correlation. And you're going to need analysis of variance as well when we use F ratios to measure correlation as well. So here we go, the introduction to correlation. When we measure relationship between two variables outside of ANOVA, sometimes we have variables that correlate to each other. That is, as one variable goes up, the other one goes up, or as one variable goes up, the other one goes down. If you're remembering this from your psych, 101, 100, first year level psych courses, or in your research methods class, great, this is going to come back to you. Again, there are characteristics of relationships that we're going to need to apply in concept. First, the first characteristic is the direction of the relationship, whether it is negative or positive. Again, you may think to, the slope formula, a positive slope or a negative slope, that's the direction of the relationship. If it goes uphill, there's a positive correlation. So let's put a plus sign there. If it goes downhill, then there is a negative correlation. Okay, it's not written here, but you'll see it later on. If it's flat, that means zero correlation. Or if the points in the scatter plot are all over the place and it looks like a cookie, also no correlation. Okay, so the direction of the relationship can be positive, uphill, negative, downhill, or no correlation, either flat or all over the place. The form of the correlation is how the variables correlate to each other. For most of this chapter in this course, we're looking at linear correlations. It's the simplest one, and that's the one we're going to use for this class. There are non-linear correlations, so there's a linear one that's just a straight line. Sometimes it's a curve that goes, one way. Another time it goes, the other direction. Now, as you can see, it's not a straight line, but the variables do follow a trend, and these are nonlinear correlations or curvilinear correlations. Finally, it's strength and consistency. So as the points are closer to this regression line, this trend, so let's say there's a positive correlation and your variables are, either close or far away. The closer they are to that trend, to that slope or regression line, the stronger the relationship is. And the strength or magnitude of the relationship has, a continuum. And the minimum is 0 and the maximum is 1. So if you ever get a test question where, can you have a correlation, at least with Pearson R, that is greater than 1? You say no. 1 to 1, perfect correlation. 1 is the max number. And you get a correlation that is less than 0. Yes, you could get something up to -1. So it could go something like this. But you're not going to get anything that is weaker than 0. Think absolute values. Think the distance away from the regression line. So here, if the distance of the points are right on the regression line, yeah, that's the strongest correlation. It's going to be 1. If your points are like a cookie, where it's all over the place and you can't really draw, and the points don't really fit in the line, that's 0. There's no correlation. The strength is 0. Again, correlation has the characteristics where the variables are independent from each other. Okay. Here's an example of a scatter plot that shows possibly a trend between two variables and showing a possible correlation. So let's take a look. Here we see a chart, and we see some students here, person A to N, and it's measuring, a person's family income and that student's average grade. Again, this is a sample we're using. Probably would not agree with this, but it's trying to get some, hypothetical or real sample data. So as you can see here, as family income goes up from 31,000, here's in thousand, 31,000 to 174. That's rich. And then you see the student's average grade. Some do better even in the low income range, but you can even see in this chart that the income seems to go up. So here you got the lowest one in terms of income, and the grade point average, yeah, it's relatively lower. And then you see someone with lots of income, and the grade point average is also higher, relatively speaking. So yes, you can still see some of them, they got high income, but the average is not as high as somebody, let's say here, 58,000 family income, but it's lower, 91. But if we put these points of data in a scatter plot, so here family income is your x-axis, student average grade is your y-axis. If we put these points in there from A to N, so here's probably A and here's N. I don't have time to draw the other points. So you can sort of see this sort of upward trend, a sort of linear relationship that's going up. And the points are fairly close to this sort of regression line, this slope, this trend, if you will. So it would show a fairly strong correlation between the two variables. That is family income in the thousands and the student's average grade. So that's how you would use scatter plots to look at correlation data. This next slide shows you a difference between positive and negative correlations, or negative and positive relationships. Again, this should be pretty quick. Here is the relationship between temperature and beer sales. Again, as temperature gets hotter, you'd probably get thirsty, and something that people would drink is beer. So as temperature goes up, more people are going to want beer, and so there's this sort of positive correlation. The next picture on the right shows you a correlation or a relationship between temperature, the same temperature that we looked at over here, with coffee sales. Coffee is here, we assume it's a hot drink, not iced coffee. And if it's hot coffee, as temperature goes up, the weather's hotter, you're probably not going to want something hot. So again, hot coffee, as temperature goes up, hot coffee sales goes down. So the first one is a positive correlation. The other one on the right is a negative correlation. Think uphill for positive, uphill, downhill for negative. Again, if you've already taken Math 11 or you know the slopes and how to calculate that, this should sound very basic, which it should, and that's great. If not, think uphill for positive, downhill for negative, going from left to right, bottom to top. Okay. Again, this is another picture to drive the point home, showing you the different degrees of linear relationships. So the first one here, A, shows a perfect linear correlation. Take a moment and tell yourself what direction the relationship is. If you think negative correlation because it's going downhill, you are correct. Okay? And because all the points are right on this regression line, the relationship here would be -1. Here for B, all the points are scattered all over the place, and this kind of looks like a chocolate chip cookie. So if the points are so spread out that you can draw a perfect circle around it and it'll cover all the points, and when you see that, the relationship here is close to 0, if not 0. So remember, think cookie, round cookie, no correlation when you see a scatter plot. Here, C is not a full circle. The points, kind of make an oval. And take a moment. Again, you can answer yourself, what direction is the correlation looking like? If you think positive correlation because it's uphill, that's correct. It's a positive correlation. And R here, for the correlation coefficient using the Pearson, R, it would not be 1. It would not be 0. It would be somewhere in the positive. I'm going to make up a number here between 0 and 1. That's important. It cannot get any higher than 1 or lower than -1. Because it's positive, it's going to be a positive number between 0 and 1. Larger than 0, smaller than 1, because the dots are not lined up exactly on the regression line. So it's a fairly strong correlation because the points are fairly close to the regression line where each point stands. I'm just drawing the distance now between those points and the regression line. And this is what we measure, by the way, when we do our regression formula as well as our correlation coefficient. But C here shows a fairly strong, or half in magnitude, positive correlation, positive linear correlation. And D here, again, it's not a full circle cookie. There is a trend. Again, take a moment to see where the trend is. If you think negative, you're right. Yeah, the points on the scatter plot seems to form a downward trend. Again, you can draw a line on a scatter plot if you can to see where the trend is, and it'll give you a good idea of what the direction of the correlation is. Again, you can see here along a regression line, or the trend, if you will, that the points are much further away in D than it is, in C. Again, in general, when you measure all the distances from the points together. This is the same technique we use, by the way, for measuring standard deviation and variance. This time we're just measuring, the points in each dot against the regression line. We'll talk more about that later. Here the relationship is negative in direction, and it's weaker than this because the points are further away from this line, the regression line. So maybe along the lines of negative 1 or 2. Again, you can see here, the closer the points are to a regression line that is not flat. A flat line means the correlation is 0. There's no correlation. Okay, so it just means like, as for example, as time goes by, if we were to use, time and age, okay, if there is, somebody who doesn't age as time goes by, there's no correlation between time and age. Like, the person would not age at all. I don't know, Keanu Reeves, if you get that reference. Or somebody that just always looks young. But again, if it's a flat line, there's no correlation. Correlation is 0. If, however, there is a slope of any kind, positive or negative, the closer the points are to that line in your scatter plot, the stronger the correlation is between 0 and 1. Again, for positive correlation, it's positive 1. For negative correlation, it's negative 1. As the points go further apart from that line, the weaker the correlation and the closer it is going to be to 0. Unless all the points are spread out like you see in B, and we just say, it's so weak, there's no correlation at all, it's 0. Okay, so how do you calculate the correlation or linear correlation? One way you can do that is to use the Pearson correlation coefficient. And here's how you do it. The Pearson correlation coefficient measures the degree and direction of a linear relationship between two variables. What this means is, if you go back to the slide with the pictures, we're trying to see what trend those points form, whether it's, in a positive or negative direction, or it could be no direction at all, and how far those points are away from this sort of regression line that we're going to predict. A perfect linear relationship means, again in basic terms, is that every change in x corresponds to the same change in y. So, for example, if time passes 1 year, okay, so if time passes 1 year, again, this is like time for x and age for y. As time passes 1 year, you age by 1 year. As time passes by 2 years, you age by 2 years. So as long as the change is consistent and they correspond to each other, that's a perfect linear relationship. So this is a R of +1, okay? Let's say if you got a case of Benjamin Button, again, you may not get that reference, but I'll show you what that means. As time goes forward, you age backwards. So let's say you start with year 1 and you're 99 years old. Year 2, you're 98 years old. Year 3, you're 97 years old. So if you already know how to do slope, hey, positive slope, negative slope, and if the slope is 1, positive 1 or negative 1, in correlation terms, that's a perfect linear relationship. And the way we measure this with Pearson correlation is with this formula here. Again, this is the concept form. R for the Pearson product moment correlation coefficient, R. We're measuring the covariability between x and y, how those two variables covariate. Divide that by the denominator, the variability of x and y separately. Okay, just like in ANOVA, we look at treatment effect over individual differences. Here, we look at covariance, the ratio of covariance over variance, or in this case, individual variance. Can't spell individual. Okay, covariance means how both variables change at the same time. The first thing you're going to need to calculate the covariance or covariability is the sum of products. This is where the sum of squares formula is going to be the foundation of the sum of products. When you look at the sum of products, it is similar to the sum of squares in the way that you're measuring the deviation scores between the value of a variable. Here is x and y from its mean score in the same variable. So for example, here is a deviation score of x values of x's. And in this section on the right, here are the deviation scores of the y values. Again, we're measuring the distance between each value, x with the mean of x, and y against the mean of y. When we multiply those distances or deviation scores together and add them up, that's when we get the sum of products. And this is the definitional formula of doing so. Again, the nice thing about this is we don't need to multiply them. We don't need to square them like we do with the sum of squares, because once we introduce another variable, the sum of products will not cancel each other out. And if it does, then that means, hey, there's no correlation at all. So we don't want to square it. We want to capture the zero if there actually is no covariance, if it actually does cancel each other out, which is why we do not square the deviation scores and we keep them as the power of 1. We don't square them, and we multiply the x deviation scores with the y deviation scores. That's the sum of products. That's going to be your foundation for covariance. Okay, so that's going to be the numerator, the top part of your Pearson R, covariance over your individual, which I'll write like this, individual variance. Okay. Here is a computational formula of the sum of products, which is the same result, but using different parts. Again, the computational formula is the same foundation as the computational formula for sum of squares. So again, the computational formula for the sum of products uses the same technique as the computational formula for the sum of squares. So here, the parts you're going to need is, okay, you would multiply your x and y scores together and then add those up. That's 1. And then here is you subtract that. Again, you're measuring deviation scores. And the n is here because, well, remember, you're getting deviation scores, which you need the mean values for, mean of x and mean of y. So to do that, you need the average technique or the mean technique, which is you add up all the scores and divide by the number, n. So here you got your sigma x and sigma y, and we use only one n here because, well, you're measuring the same group but with 2 variables, so the sample is the same. This is kind of like a repeated or related sample study. So this is the computational formula, and you don't need to get all the deviation scores using the computational formula. All you need are the sigma xy, where you add up all your x's and y's first, and then you multiply your x and y's in each variable first, and then you add them up, and then you subtract that by your sigma x times sigma y and divide that by n. Again, when you do the practice worksheets, you can apply these in your computational formula, and that's the one you're probably going to use most of the time. Again, both formulas work though, so when you do your test, and if you've practiced enough and you've given yourself extra time, start with your computational formula, get some numbers first, and then double check it with your sum of products, your definitional formula, just to really make sure you got the right sum of products if you need to. Once you've figured out your sum of products, you're halfway done. Then you can calculate your individual variances, which are sum of squares, right here in the denominator. So you got your sum of squares for x, multiplied your sum of squares for y, and you square root that because we are measuring standard deviation, or variability in this case. Remember, your sum of products is not squared. Not squared. You're not multiplying sum of squares, you're multiplying deviation scores, which is why it's called sum of products. Okay? And so when you measure sum of squares, you've already, squared everything, so you must square root the variances that you're going to get. So again, the Pearson correlation calculation, when you calculate R, you get your sum of products at the top, and that's your covariance. And then you divide that by individual variances right here. So be sure to get your sum of squares for your x's and y's, which you should know how to do on your own by now, and then multiply those and square root it. Okay? So you'd square root the variances to get standard deviations. Okay? So here's an example of this. You can actually try this at home with plotting the numbers. So here's a scatter plot, and for a moment, try to plot the data and the numbers. So here you got x and y. I'm just going to do this quickly. So the first value here, x is 0, y is 2. So that's done. Here you got x is 4 and y is 2 again. Done. So 0 and 2, 4 and 2. Here, we got something here. It doesn't look like a function to me, but anyway, we'll roll along with it. 8 and 4. X is 8. Y is 4 again. That's weird. 8 again and 6. Okay, and the last one here is x is 10, y is 6. Okay, so you got your variables here, x and y, and you can calculate the totals, the means, and the sum of squares, and so on. So you can try this and practice it and see if you can find a correlation coefficient using the sum of squares, your mean, and then the sum of products, and then calculating your R as the final thing here. So for example, the total here would be, here's y is 20, and this is your sigma x, sigma y. Here it looks like 16. Here's 20 again. Am I right? Nope. I'm done. 30. Okay. And so you can get the mean from this, or x bar y, x and y bar. So here, it's 30 divided by 5, that's 6. Here, y is here, 20 divided by 5, that's 4. And you can go on to calculate sum of squares for x's and y's, and then sum of products, and so on. So again, for your xy, you would multiply xy together. Here's 0, here's 8, not 6. Here's 32, here's 8 times 6, that's 48. And then 60. You'd add those up and have a total, and that would be your sigma xy. So here's another note here for Pearson correlation and z-scores. Because z-scores measure the number of standard deviations scores away from the mean, you can use z-scores to get the correlation in the Pearson correlation formula as well. So you can use the same formula and express it as a relationship of z-scores. So again, you can get your sum of products at the top expressed in z-scores. And then for samples, because we are looking at samples, we account for sample bias or sample error. So that's n minus 1. For the population, this is row this time, actual row. And in ANOVA, this n looking symbol, that's eta. In correlation, for population correlation with the Pearson correlation, this Greek symbol here is row this time. I'm trying to get this right. So population correlation coefficient. So here we use big N because we're looking at the population, dealing with parameters. And so this is what we're going to use to test whether there is a correlation in the sample by, doing a z-test or t-test to see if there is a correlation. So again, your Pearson correlation formula can be expressed in z-scores or even t-scores. So we're going to end this first section with a learning check with our questions. So here's question 1. It reads, a scatter plot shows a set of data points that fit very loosely around a line that slopes down to the right. Which of the following values would be closest to the correlation for these data? Again, the scatter plot reads very loosely around the line that slopes down to the right. Take a moment and choose your answer. So you got a line that slopes down to the right, and the points fit kind of loosely like that. So that's what that looks like. So not a round cookie, but maybe an oval cookie. And so again, the sign indicates the direction. If it slopes down, is it a positive or negative correlation? If you think negative, that's correct. Slopes down, downhill, negative correlation. And because the points are fitting loosely, that means not close to that line. It's closer to 0 than it is to 1. So if it's a 0 for R, that means it's weak or no correlation. If the R is closer to 1 or at 1, that means it's strong. And if it's 1, a perfect correlation. Okay, you can think back to that time and age example as a perfect correlation. As time goes 1 year, you age by 1 year. Not everything has that perfect correlation. So that's why we have, distance between 0 and 1. Again, the direction could be positive or negative. That's why R is either between, including -1 and +1. 0 being the weakest of the strength being no correlation. Okay. Next question. Decide if the following statements are true or false. Here's a two-part thing here. A set of n equals 10 pairs of x and y scores have the following, characteristics. Sigma x is the same as sigma y, is the same as sigma xy, and they're all equal to 20. With this set of values, the sum of products, SP, is equal to -20. True or false? Number 2, if the y variable decreases when x variable decreases, the correlation is negative. Take a moment to figure out your answers. With A, you're probably going to need more time, as well as the sum of products formula, which I'll just go back to here. This one. Again, we can use the computational formula. So remember, your sample is 10. I'm just plugging the numbers in. If you already figured it out, great. All these values are 20. So you have 20 minus 400 divided by 10. Here you got 20 minus 40, and that is -20. So if you answer true for part A of the true-false question, you are correct. So you can see here, if you add up all your x scores and all your y scores, and if you multiply your x, y scores together, so you might make a chart like this. Okay, let's say here like that. Perfect correlation in the positive direction. 1, 4, and 9. So again, you can add those up. Okay, so it would be, for example, 6. I'm using this data set now. 6 here, and then this one would be, because I multiplied them first, add them all up together. Here's 14. Okay, so you would have its own values. This one just happens to have all equal values. That's going to give you a unique sum of products. But yes, once you figured out what sigma x, sigma y, and sigma xy is, you can get your sum of products using the sum of products formula. And for B, yes, it's false. If you think false, you're right, because if both variables decrease, even though they're both going down, the direction matches. So when the both variables change in the same direction, it's a positive correlation. Okay, just think that uphill downhill for a second. So again, the uphill downhill applies to the scatter plot. So remember, in the axes, okay, so if it's an uphill, both variables are changing at the same direction. Again, if they're decreasing in the same direction, it's still the same slope. You're just looking at it in the other, going the other way. In the negative correlation, that means as one variable goes up, the other one goes down. Here, let's say as time goes up, age goes down. In a negative correlation, that's like, again, Benjamin Button, if you get that reference. Somebody looks younger as time goes by. In a positive correlation, as time goes by forward, the person looks older. So again, if both variables change in the same direction, for example, somebody looks older as time passes, then it's a positive correlation. Same direction, positive. So again, same direction for both variables equals positive correlation. If they go in the opposite direction, if the variables change in the opposite direction, I'll write this fully here, and then that would be a negative correlation. Most of you probably already got this by now, but if you still find yourself stuck, just try a few examples. Maybe use time and age, or height and shoe size, or something that you can check the correlation. Think back to your math in terms of calculating slope. Positive slope means positive correlation. Negative slope means negative correlation. A positive slope means both variables change in the same direction. A negative slope means that the variable, one goes up, the other one goes down. They change in the opposite direction. So that's it for today, I think. Let me double check here. Yeah, again, we're 68 slides in total, and we've done our first 18 slides. So in our next section, we're going to talk about how to use the Pearson product moment correlation, or Pearson correlation, to predict outcomes, test validity, test reliability, and verify theories. That is to see if there is a relationship between two variables. So until then, start on those practice questions, and you can do at least a few of them now, maybe even up to number 5 or 6. Okay, try those practice questions as much as you can. Read your textbook. Try those questions on your Canvas modules. Again, you can either find the module in the announcement or all the way at the bottom. Use Microsoft Edge or Safari if you want to try these web tutorials. Again, it doesn't work for Chrome. I'm using Chrome right now. And you can always double check, your concepts with glossary and flashcards. So there you go. Again, if you got any questions, you can email me directly or message me on Canvas. Leave a comment on YouTube if you feel like that. But again, the direct ways of contact are email and Canvas messages. We'll see you in the next one. You can do this. Let's keep going.